This video is about modeling a plug flow reactor. Which is a tube. I'm just going to draw its side profile. And the simplest thing to model is probably a first order irreversible chemical reaction. A goes to B. I'm going to define a coordinate system where x starts at the left side, so x equals 0 at the left side, and the length is x equals L on the right. I'm going to assume that the tube has a constant cross-sectional area. I'm going to call it A sub C. I'm going to assume that A, being the reactant, flows in the fluid that enters at x equals 0, and that there's no B in this fluid. So additional assumptions are that we have no axial gradients. What I mean by that is that if I pick a value of x, there is no difference in concentration between the fluid that is at the center of the channel and the fluid that is at the walls. In other words, the following variables, Ca, Cb, T, etc., are dependent on x only and not on radius or r relative to the center of the tube. That's actually not a physically reasonable assumption, but let's make it for simplicity and illustrative purposes. Okay, so additional assumptions right now, I'm going to assume that we have constant temperature. In general, if you have an exothermic reaction, for example, we could have a heat of reaction that affects the temperature of the fluid as the reaction progresses, but I'm going to ignore that in this problem. The other thing is I'm going to assume steady state, which means nothing depends on time. In my class, my numerical methods class, we start by studying ODEs, which means that we're only looking at differential equations in which things vary with one variable at a time. This is why we don't consider variations in time and variation in position at the same time. In general, things, of course, can change in time and position, but we're mainly just interested in understanding how to formulate a differential equation, so we're only going to consider one variable at a time. And I'm going to assume that fluid density rho is constant. Okay, so what are we trying to do? I want to formulate a differential equation that could be solved. We're not going to talk about solution methods, but something that could be solved to calculate Ca of x and Cb of x. And in order to do this, we're going to have to use differential control volumes. So coming back here, I'll pick a color. And so what I mean by a differential control volume is that a control volume that is cylindrical in shape starts at x and ends at some incremental step later, x plus delta x. And so let's draw our control volume. So it looks like this. It looks like a cylinder. We have fluid flowing in. We have a constant cross-sectional area A sub C, which would be pi r squared. And we have fluid flowing out. This control volume starts at x and ends at x plus delta x. So let's start by doing a balance on fluid. So the balance on fluid is not very interesting because density is not changing, but it's a good place to get started. Accumulation equals input minus output plus generation minus consumption. And these need to balance. Accumulation is always a time-dependent quantity. It's how much something changes over time. In this case, how much fluid builds up in the control volume over time. And since we're at steady state, nothing can change with time. So we know that accumulation is 0. So 0 is going to equal, so what goes in? Well, the rate at which fluid goes in is, so I'm actually going to do this in terms of mass, by the way. Technically, mass is conserved, volume is not, but we'll see that that actually doesn't really matter right now. So the mass flow rate going in is going to be F, the fluid flow rate, which we say it's F in at the beginning, but at this point over here, we're not assuming that the fluid flow rate is F in, although we'll find out it actually is. Rho F evaluated at X minus rho F evaluated at X plus delta X. So if you think in terms of units, F should be volume per time, say liters per hour. Density is going to be mass per volume, so the units we're looking at is mass per time. There is no generation. Generation is 0, and consumption is 0. And so because density is constant, we can actually cross it out. We can divide everything by 0. And what we end up getting is the following: F at X plus delta X minus F at X. So I moved them to the other side, equals 0. I can always also say that I multiplied by a -1, right, to make this term positive and make this term negative. Because I have 0 on the other side, I can multiply by whatever constant I want. I can also divide by delta x, because 0 over delta x is still delta x. I can take the limit as delta x goes to 0, and what I get is df dx equals 0, which effectively means that f is constant, or that f is equal to f in. Because it starts at f in and it's constant as x changes, then we know that fluid flow rate is actually constant. So as I mentioned, this is not very interesting, or surprising perhaps, because density is constant, the fluid flow rate ought to be constant. So now let's do something that may be more interesting. Is balance spelled with an A or an E? I can't remember. Maybe it's an A. Okay, so we do a balance on A, and again, accumulation equals in minus out plus generation minus consumption equals accumulation, which is already there, and it's equal to 0. Remember that we have a chemical reaction A goes to B and a kinetic constant K. So the accumulation on A is 0. We're using the same control volume, so this is the control volume. Fluid is flowing in and containing A, so that would look like FCA. And then it's flowing out. Again, we'd have an FCA term at X plus delta X. The input occurs at X. And in the volume of our control volume, so throughout the cylinder, there is a chemical reaction that consumes A. So there is no generation. Generation is 0. The input, So I'm going to say 0 equals, the input is going to be FCA at X. And so that is going to be, F has a volume per time unit, Ca has a moles per volume, so that looks like moles per time or number of molecules per time. The output is going to look like FCA evaluated X plus delta X, and the consumption is the rate of reaction, which is KCA, and that is going to be in a per unit volume per unit time basis. So to get the units to work out, I have to multiply by the volume of the control volume. So I'm going to say AC delta X. That's the volume of the cylinder. And so I'm going to move these terms to the other side. I'm going to divide through by F, and I'm going to take the limit as delta X goes to 0. So the limit as delta X goes to 0 of F at X plus delta X minus F at X divided by delta X. Did I say I would do that? Yeah, I'm going to do that. Is equal to minus K over, or KAC over F times CA. Let's see, I divide by the delta X divided by F. I think that is correct. Okay, and this is going to be dF dx. So our differential equation, whoops, no, this is wrong. I said I divided by F. This should be CA. Sorry about that. This should be CA. And so the differential equation is dCA dx equals minus KAC over F times CA. A reality check may be useful. So intuitively, we know that as we go across the reactor, A is going to be consumed. And so we would expect dCA dx to be negative. And in fact, the rate at which it changes should be proportional to Ca. So in the beginning, it should change faster than at the end because Ca is being consumed. So let's take a look at that. So dCA dx, these quantities, in fact, so is this, they're all positive. So this negative sign means that we have a negative derivative for Ca as function of x. And so that makes sense. Also notice that the rate at which Ca declines is going to be proportional to Ca. So I'm not going to do the balance, well, maybe, never mind. I will do the balance on B. I'm going to abbreviate balance so I don't have to remember how to spell it. So it's going to look exactly the same as the balance on A. The accumulation is 0. This is going to be FCB instead of FCA. This is going to be FCB instead of FCA. But the rate of consumption is going to be KCA, because remember that this reaction rate, which consumes A, also produces B, and the rate of reaction depends on Ca, not Cb. So in fact, I'm glad I'm doing this. Okay, so accumulation is 0. So the input at X is going to be FCB at X minus FCB at X plus delta X minus KCA AC delta X. Whoops, not a minus, it's a plus, because it's going to be generation rather than consumption, because the reaction over here is generating B. So that's going to be positive. Okay, so now if we rearrange things in the same way, we should get the limit as delta X goes to 0 of CB at X plus delta X minus CB at X divided by delta X is going to equal positive KAC over F times CA. This is dCB dx. So we're going to have a pair of differential equations. I'm just going to copy, well, I'll move it. So our system of equations that we're going to need to solve, in fact, why don't I just copy this again? So if I change this to CB, I just have to change that to a positive, and this is our goal. These are the differential equations that would need to be solved in order to calculate the profiles of concentrations of Ca, or concentration Ca and Cb in the PFR.